All right. So, um, so the next section is we're going to talk about actual fibers. So the reason why we talk about fibers a lot is because it's hugely used in all sorts of different applications. So the initial area where it was the most used was telecom for communications because it's a really good alternative to electrical cables. But now in biomedical optics, it's highly relevant because yeah, it has a lot of advantages that can be put to good use, which we'll discuss in a second. So an optical fiber essentially is the cylindrical version of the planar waveguide. So instead of being this slab of material that's infinite in two directions and then finite in one, we now have a cylinder where you have in the middle a core with a certain index, and on the outside a cladding with a different index. Now, in fibers, one of the terms that is hugely important, which comes back all the time, is something called the numerical aperture. Now, the numerical aperture describes the acceptance cone of the fiber, meaning which light can be accepted and will be guided by the fiber. So essentially, what it does is its equation is written here. So it's N0, where N0 is the index of the external medium, so not the fiber itself. So the point being here that the numerical aperture of a fiber changes depending on its medium in which it's located. So if the fiber is in air, N0 is 1. If the fiber is in water, the N0 is 1.4 or 1.3 something. And that can change. So the acceptance angle of a fiber will change depending on the medium in which it's located. Oh, and actually, so what it describes is the maximum angle that a ray of light can hit the fiber and still be accepted and guided by the fiber. Okay. So this here also takes into account the initial refraction which occurs at the interface between the beginning of the fiber and the external medium. Okay, so why is fiber so interesting? The primary reason is that fibers can transmit signals over huge distances. So for example, typical values is this thing that we call 0.2 dB per kilometer. So dB is the logarithmic decibel scale, which means that you have this value 10 to the power of this value divided by 10. And so, for instance, what that means is if you have a 0.2 dB attenuation per kilometer, it means that after 15 kilometers of fiber, you will still have 50% of your power. After 100 kilometers, you will still have 1% of your power. Then the other advantage is that the speed of light is still faster than the speed of electrical signals in coax cable and electrical cables, for instance. Now, this is super interesting, because of the fact that it transmits over very large distance. And it's used, for example, I'm sure you all know that there are huge fiber cables that run at the bottom of the Atlantic. And every about 70 kilometers, so the signal in the fiber, because there are some losses, and for the reasons for those losses are what we talked about in the beginning. So there is total internal reflection, so theoretically all the light stays inside, but because of the imperfections of the fiber, some light is still lost, which results in this 0.2 dB per kilometer loss. And so at the bottom of the Atlantic Ocean right now, you have these huge fiber cables, and about every 70 kilometers, there's an amplification system that re-amplifies the signal so that it can be transmitted another 70 kilometers. But you have to imagine that if you tried to transfer signals with electrical cables, you have, 6 dB is, it's significant. Like you could probably go 1 kilometer or so, and then you would need to have some kind of amplification before your signal, otherwise your signal would be lost. So you'd have to have amplifications every kilometer crossing the Atlantic Ocean. Just an example of why fibers are so useful. So you have different types of optical fiber. So you have the two primary types, which we'll discuss in a second, are called single mode and multi-mode fibers. So in the planar waveguide that we talked about a few minutes ago, we saw that there are different ways that the ray can propagate, different modes. In the single mode fiber, there is a single way, there's a single path that the light can be transmitted. And then you have the analogy of the fiber version of what we just talked about. You have gradient index multi-mode fibers. So what is, and then there's of course a whole bunch of other fibers. There's polarization maintaining fibers. There's multi or double clad / multi-clad fibers. There's fibers with all funky geometries that have that alter. So the geometry of the fiber and the index profile alter how the mode propagates, and depending on what you're looking for, all these different variants can be interesting. But for the time being, we're going to focus only on the single mode, multi-mode, single mode, and multi-mode, and understanding the difference between those two. So what we just saw, so this is a representation of a fiber. So it is a cylinder, but we're just showing it as a slice. And it looks exactly the same as the planar waveguide that we saw a little bit before, right? So you have this core index region where you have one value of the index, the core index, and then you have the cladding on the outside. Now, in this, you have different angles at which the light can travel, and therefore different modes. Now, in the SMF, in the single mode fiber, which are much smaller. So we're talking cores that instead of being 10, 20 microns, 10 microns to 1 millimeter in diameter. We're now talking cores that are 3, 4, 5 microns in radius. So let's say 6 to 10 microns in diameter. There is a single possible path. Now, this is where the geometrical interpretation that we just saw fails, because we still have, technically, we still have a core index, we still have a cladding index. So why can't total internal reflection happen inside this fiber? Just because it's smaller, it doesn't really change the fact that this angular analysis should still work. And that's where it stops working, because you can't consider light as just rays. You have to consider the wave nature of light. So when you have single mode fibers, which are much, much smaller, you have to consider the wave, the wave nature of light, and that actually limits the different paths that light can take. So without going into all of this, but basically you have Maxwell's equations, which describe basically any electromagnetic field in any environment. And if we make certain assumptions that are specific to the fiber, so non-magnetic, non-conducting, locally isotropic, you can reformulate the expression for the electric and magnetic fields inside the fiber as the following in Fourier space. Making some further assumptions, making some further assumptions and changing the equation to describe the index profile. You can change the equation into this, and then what we need to realize is that in a fiber, there is a transverse component to the field. So there's the electric field has one description, which is for one slice of your fiber, and then it has an evolving term. And basically, you play around with the math some more, and you end up with this equation right here. This equation describes only the transverse electrical field. When you solve it, or if you try and solve it for different index profiles here, so you have the n squared r here is the index profile, phi is the field, and beta is the propagation constant of your mode. If you try and solve it, what you realize is that there are only certain values of beta which can solve this equation. And in the case of single mode fibers, you actually have a unique solution. So there is only one value of beta of the effective index, the invariant, that solves the equation. Therefore, there can only be one mode in the single mode fiber. Okay, so the key takeaway here is that when you go to very small fibers, you have to take account the wave nature of light. You do this by solving Maxwell's equations, and solving these equations comes out at the end that you have not an infinite number of solutions, but you have a discrete number of solutions. And in specific geometries of single mode fibers, you only have a unique solution. Okay? So when you have multi-mode fibers, so you still have several solutions, there's still a discretization of the possibilities. And these show up as these funky patterns that you see here. So now instead, if you imagine the scenario where you're shooting light into a fiber, what's going to happen is instead of taking any random angle and being a ray, as we saw before, it's going to excite a specific pattern or several patterns in this fiber, meaning that part of the energy is going to be put into this pattern, part of the energy will be put into other parts, and you have a linear combination of those. And what that physically looks like is something like this. So what the person is doing here is they're just changing the angle and the position at which light is being shot into a fiber. And you see that what's coming out of the fiber actually has these funky shapes. Okay, and so using this wave theory, you can still come out with different values of beta, different values of the effective index, and you still have these effects that we talked about previously, like modal dispersion, different propagation times, propagation speeds, and so on. It's just that there, instead of being an infinite number of possibilities, there are discrete values which this can be, and those are called the modes. Okay, so one of the tools that you may have to use at some point in your study is the normalized fiber frequency. So when you do all the math associated with these modes, and you solve the Maxwell equations, and you solve the field equations in the fiber, there's a way of turning it or reformulating it such that you calculate this value here, the V number, right? And you calculate the V number simply by taking these parameters, which you can know about a fiber, which often given in the spec sheets. And then you consider this curve right here, which is called the UV curve, very original name. And if you look at a specific value of the V number, and you draw a vertical line, the number of lines that it intersects with will tell you how many modes exist in that fiber. Okay? And what's key here is that if your V number is below 2.405, you will only have one mode, so not the diagonal one, but just all the other lines. You'll see that, for example, if your V number is 2, you only intersect with one line. Therefore, you only have one possible mode in your fiber. And this mode is called the LP01. If we go back, the LP01 is actually this one right here, right? If you increase the V number a little bit by either reducing the wavelength or increasing the core radius or the numerical aperture of your fiber, and let's say you go above 2.405. Then you have a second mode, which is the LP11, which is this one, right? And that's crucial because in a lot of applications, you need to use single mode fibers because since there's only a single propagation mode, we don't have all these problems that we talked about previously where different modes propagate at different speeds, therefore your pulses get broadened. You can't do any interference measurements with multiple modes. And so you're always going to be using single mode fibers. Okay? So for large values of V, so when you're using larger fibers or wavelengths that are very, very small, you can estimate the number of modes inside your fiber using this equation. Does that make sort of sense for everybody? Are there any questions or is anything unclear regarding single mode fibers, multi-mode fibers, why we're talking about the wave nature and so on? Okay, so far so good? All right, so that describes, so it's a whole field, the analysis of fibers is a whole field, and the field inside fibers, you can do a whole bunch of interesting things with it. And the result of that, is some essential fiber components, which you may come to use in setups that you may build further down the line. Some of these are the following. So you have power splitting couplers. So power splitting couplers do exactly what their name says. If you send, let's say, light inside this branch with the red arrow, that light will be split into the two output branches, or it doesn't have to be two, it can be n output branches with a certain ratio. And so you can have 50-50 couplers, 90-10, technically any ratio in between 0 and 100. What's also very interesting is that when you combine, when you use both inputs of for example, a 50-50 coupler, the fields that, so the electrical fields of in each branch are added in the center of, which means that the interference can occur in the center of the fiber coupler. That's super relevant in OCT, for example, because I'm sure in your OCT class you saw that OCT is just a Michelson interferometer, and the interference happens when the two beams are mixed back together after coming out of the beam splitter. And essentially, what you're measuring is the sum of the fields, and then you take the norm square, the square of the norm of that field, and that's the intensity that you measure. Well, this interference effect occurs also inside this this couple. Another interesting component is a fiber circulator, which is essentially a roundabout for light, meaning that if you send light into port 1, it will come out of port 2, and if you send light into port 2, it will come out of port 3. And so that's actually very useful in fiber setups, and we'll show one in a second. And yeah, they use something called the Faraday effect, but we're not going to get into that. Another very useful component is the fiber Bragg grating. So if you inscribe index dips inside the core of your fiber, this can act essentially as a Fabry-Perot interferometer or echelon. Does anybody want to take a chance to explain what a Fabry-Perot is? Wow, so many volunteers. All right, so a Fabry-Perot, what happens is when you put two mirrors very close to one another, and one of the mirrors is partially reflective, so it transmits also part of the light. And then depending on the distance, if you send a beam of light through, there's going to be constructive or destructive interference depending on the wavelength of the light. So if the mirrors are exactly a multiple of the wavelength apart from one another, then you get this constructive interference, and that light will be constructively interfere and will come back out because it's not And if you have any other wavelength, the the light will not constructively interfere, and therefore the amount that comes back out is strongly minimized. So what happens here is kind of the same thing. So by each one of these little dips acts as a little mirror in a sense, because it's the same thing as Snell's law. Is as soon as you have a mismatch in index of refraction, part of the light will be reflected back and part of the light will be transmitted, which you can calculate with the Fresnel equations. And by lining them up like that, what happens is that the light that's bounced back from each dip for a specific wavelength, where that matches the this alpha parameter here, or delta. Oops. If the wavelength matches this distance between the dips, the reflected light will constructively interfere, and so there will be a much stronger signal for one specific wavelength, which is what the little diagram shows here. So if you send a broadband signal in, most of the light will just go through, but the light that is constructive, that interferes constructively as it reflects, will be strongly sent back. Okay. Another example that's very useful is a wavelength combiner. So by fusing two fibers together in a specific way, you can combine two wavelengths together. And so what you have to understand here is that because the mode constants, the beta values are different for different wavelengths, and let's say you're taking two different fibers and fusing them together, you have no guarantee that this final fiber at the output will guide effectively all the wavelengths, right? And more importantly, in biomedical applications, or in a lot of applications, you have no guarantee that it will do so in a single mode manner. So let's say you try and combine, I don't know, a light from 400 nanometers and a light from 1300 nanometers. If you combine them into the same fiber, that's quite easy and quite possible, but it's going to be very difficult to do that such that both wavelengths are single mode. And then one wavelength, let's say 400, might be multi-mode, and then you can't do, and then you have all the problems of multi-mode propagation again. Okay, so what happens in these components, in this wavelength division multiplexer, or in the other components as well, is that when you fuse two fibers together, depending on how you fuse them, you solve again Maxwell's equations. And by stretching them a little bit more, fusing them over a longer distance, pushing the cores closer together, the field will actually go from one fiber to the other. So the simplest example, for example, is the power splitter. You fuse the two fibers together, and part of the electric field in one fiber, if it comes close enough to the other, will jump to the other fiber, and vice versa. And by adjusting how close you bring them together, how long they're close to one another, you can control exactly how much light jumps from one to the other, or which percentage of light, and then you have these splitter ratios. Okay, and the same analysis can be done for wavelength combiners, but instead of looking at the power combination, now you're looking at how effectively one wavelength jumps from one fiber to another. Okay, any questions on these components? Okay, so the setup I know very well, and that you've seen in your classes, is an OCT setup. Does this look super unfamiliar to anybody? Has Professor De Boer shown similar diagrams? No?
Yeah, simpler ones, Xavier.
Oh, okay.
With only one splitter.
Okay. All right. Well, so I'm just going to go through it just to show you the utility of these different components. So in your OCT class, you talked undoubtedly about swept source OCT, where the wavelength is sweeping, the laser is sweeping across the wavelengths. And then you have, so if the light comes out of this laser, what you have here is a 99-1 coupler, meaning that 99% of the light will go into this top branch, and 1% of the branch will 1% of the power will go into this bottom branch. Now here we have a fiber Bragg grating, which we made exactly such that only, let's say, light at a specific wavelength is going to be reflected backwards, right? So what happens for the swept source OCT is that it sends, let's say it sweeps from 1200 to 1300 nanometers, and this fiber Bragg grating only reflects light at 1250. Every time it sweeps, there's going to be a pulse of 1250 light that goes back to this detector. And this can act essentially as a sweep trigger. So every time it does a sweep, this detector here will receive a pulse, and that's one way we can know that it's sweeping. Okay? So afterwards, you go to, again, this power splitter, where the purpose of this one is to split the power between the reference arm and the sample arm. And here, these two circle components, those are the circulators that I mentioned. So those are the roundabouts. So what happens is light in the reference arm here comes from the splitter, comes here, travels to the reference arm fiber. Then we shine that light onto a mirror, it comes back, and then instead of going back through here, it goes downwards to the rest of the setup. And you do the same thing in the sample arm. So the light travels from the splitter to the sample, back and downwards. And then finally, you have another power splitter here where the purpose here is not really to split, it's to combine the two signals in order to do the interference. And so this OCT is just a good example because it uses a lot of these important fiber components. And the advantages or the reason why we want to use so many fiber components in BMO is because they have a number of advantages over free space operation. So free space is when you have light that's traveling just in open air, and it looks something like this, right? So you have a lot of mirrors, lenses, and so on and so forth. The problem with this is it's bulky, and then it's also very sensitive to any kind of vibration. Somebody bumps into it, a mirror moves a fraction of a degree, and now your laser is no longer aligned and nothing works. In the case of fiber, you don't have that as much because you can touch the fiber, you can lay it down, pick it up, lay it down. The light is still going to stay inside, and therefore you have a much higher degree of robustness. And so in clinical setups, so setups that are meant to be used by doctors, fiber has a huge advantage of robustness. Another very big advantage is safety. So lasers can be quite dangerous. Having lasers in free space can be dangerous because let's say someone puts their arm in there and the laser is too powerful, well, they might burn their arm. You know, it's not no like Star Wars type lasers where it's going to cut your arm off, but it can damage your skin. Or if someone's wearing a ring or a watch and they pass in the laser beam, that laser reflects off that metallic surface into someone's eye, can damage the eye. And so when you have it in a fiber, all of the fiber talks that we've had right now is always core and cladding, but you can always wrap the fiber with some other protective material, and then the little light that does escape cannot escape in any dangerous way and damage your eyes. And finally, probably the two biggest advantages are flexibility and size. And so a fiber, I don't know if you've ever had the chance to touch an optical fiber, but a bare fiber is around, let's say 100 microns, 125 microns in diameter. That's about the width of a human hair. And so something that small can very easily fit into all types of small holes in the human body. So you can stick fibers into someone's nose and ears. You can insert fibers into needles and then use the needles to get wherever you want to in the body. And so it has a lot of advantages for minimally invasive imaging or sensing. Okay, so far so good. Any questions? All right. So some of the examples that we can give for the application of fibers in biomedical optics. The first one is a fiber bundle. So imagine you take thousands of fibers, and you pack them all into one bigger bundle. What's interesting is that if you place some imaging optics, you place it in front, and then you have your sample. Any light that emerges from this particular point in the sample is going to be collected by one fiber in this whole big bundle. And the point next to it is going to be collected by the fiber next to that, right? And so what happens now is that this full image can be transmitted. This full image can be transmitted along this fiber bundle, which can be an arbitrary length and can also bend quite a bit inside the human body. And you can basically use that to go image inside the human body where this fiber bundle would fit. One of the advantages of this is that a fiber bundle, even if you have thousands of fibers, is still going to be smaller than miniature cameras. So then miniature cameras, I don't know, I'm not an expert in the field, but the smallest ones are usually around 5 millimeters, 6 millimeters, and fiber bundles can be much smaller than that, therefore giving you access to certain areas in the body that you wouldn't be able to get access to with other devices. Okay, so just to give you a little example of this, this is an image from a company, Cylindrical, and they do lung imaging, and where the fiber bundle is located inside this needle. And you can actually you can use this to image individual cells. So this is fiber bundle based confocal laser endomicroscopy. And this allows you to really image individual cells and see cell nuclei and cell walls and so on and so forth. And so what we have here is you can see at cellular level inside the body without having to cut something out and put it under a microscope. And this could be super useful in terms of detecting a cancer or evaluating the stage of development, and that's just cancer. There's 100 other potential applications to it. So another big applications of fiber in biomedical optics is optical coherence tomography. So in OCT, you can use fiber to make your setup, which gives it more robustness. But you can also use it in your sample arm to be able to detect or image samples that are at inconvenient locations. So let's say the esophagus, the lungs, inside coronary arteries, and so on and so forth. And so this slide here shows a bunch of different endoscopes that use optical fiber. What happens here, for instance, in this top left one, is you have the fiber coming here. You have some miniature lenses that focus the beam, and then the beam is sent sideways out of the catheter, and this little catheter will rotate, and that's how you generate the image, the OCT image. And these catheters can be millimeters in diameter, like 1 or 2 millimeters in diameter. Some have even gone smaller. And so you can potentially do imaging inside a beating heart because the catheter is so small, and it's been done before. An alternative is these tethered capsule endoscopes, where these are basically big vitamin pills that you swallow and that are tethered, so hence the name, with a fiber. And so the fiber goes in with the capsule, and there's a little micromotor inside the capsule, or the fiber is spinning, and that again creates this cylindrical imaging of your esophagus. And then you can do OCT like that. Okay. Yeah, here's actually a little image. So this is an example of how OCT works based on these fiber endoscopes. So this is in the esophagus. And so these devices allow you to make complete scans with these advanced imaging technologies of these inaccessible organs. So you can use technologies and techniques like fluorescence imaging, OCT, confocal laser imaging, and even some therapeutic techniques like laser ablation inside the human body without having to cut anybody open. Or if you do, you're only making minimally invasive surgeries. Another technique that's actually being developed in the Amsterdam UMC by Professor Faber is called single fiber reflectance spectroscopy. So by using a single fiber, so a standard spectroscopic technique is called diffuse reflectance spectroscopy, where you use one fiber to send light onto your tissue and another fiber to collect it, which is located at a certain distance. And basically what that allows you to do is it allows you to detect changes in the optical properties of your sample. And by detecting these changes in optical properties, you can infer changes in the physiological state of the sample. And this, again, uses fiber optics. But what's developed here in Amsterdam is this technique called single fiber reflectance spectroscopy, where you only use a single fiber to get for both illumination and collection. And this allows you to, again, assess the optical properties deep inside, potentially deep inside the human body, and extract meaningful information that you couldn't access with a standard camera, for instance. So another thing that's interesting about the fiber tools is that it allows us to combine various techniques. So I showed you one of these essential tools, which is the wavelength combiner. So the most basic application that you can do with that is do imaging at 2-3 wavelengths. But you can also use them to combine different techniques. For instance, here, the researchers combined OCT with fluorescence imaging. And fluorescence imaging can be an indicator of vasculature. So if a fluorescent dye is injected, it gives you a better idea of where your vasculature is at. You can also combine it with these different fibers. So the double clad fibers, for instance, that's something that I'm working on personally. And using these double clad fibers, you can do the color imaging or the spectroscopic imaging at the same time as OCT, but you can also use it to do OCT and therapy. So in this little video you see here, on the left is the OCT image, and on the right is a standard camera. And basically what's happening is we're blasting with a very high intensity laser and coagulating the tissue at certain locations, those little white spots that you see appearing. And what's interesting for that is that using OCT, you can monitor how deep your ablation laser is affecting your tissue. Now, let's say you had a tumor that was a certain depth. You could increase or decrease the power in order to affect a deeper or more shallow zone, and therefore have a more controlled ablation zone. All right. Yeah, this is the same example as the very beginning. So another combination of techniques is OCT with the single fiber reflectance spectroscopy, where we do white light spectroscopic imaging. So we acquire the OCT image, which is the black and white images that you see here. And then we acquire spectroscopic information from a white light source, which allows us on one hand to reconstruct the color, which is what you see in the middle image, but also the spectroscopic information, which can be used to extract. This, for example, is the absorption at one wavelength, at one specific wavelength, which corresponds to an absorption peak of blood. And what this image shows is an inflammation area, which extends wider than just the area of the wound on the skin here. Just another example of a potential application. Okay, so it's been a very broad overview. We haven't gone into too much depth on any of the subjects. Do you guys have any questions about the fiber stuff, the guided optic stuff, the potential applications, and so on and so forth, before I talk a little bit about the assignment. All good? No questions? Okay, so the assignment. So here you guys are quite a few, so it's going to be teams of 4 or 5 rather than 3 or 4. Dirk, is that correct, or?
No, I think 5 is a little bit too much. I would rather have 3.
Okay. Well, we'll figure that out.
Yeah.
So what's going to happen is you're going to receive a short proposal, a short description of a clinical problem. You're going to, so it's either a disease that needs to be detected or a disease treated or something like that. And in your team, you will have until, so don't mind until tonight, midnight. Dirk and I will figure out the exact deadlines. But you'll have a relatively short amount of time to submit a 1-page proposal on how you're going to address these problems with concepts that were seen throughout your entire class. So not just from today's class, but from the whole BMO course. What's going to happen is I'll evaluate these 1-page proposals, and I'm going to challenge you on all scientific, so physical and technological aspects. So I'm going to ask some questions. How would you do this? How does this work? Have you taken this into account? Different constraints, and so on and so forth. And then you'll get a certain period of time to iterate on your design, and in the end submit a 3 to 5 page report, which gives a more in-depth description of your proposed design. Okay, and so one of the objectives is to, like it's written, is to become aware of also the technical difficulties. So you've learned a lot about the theoretical, how each of the different modalities or different techniques work. But what I'm going to challenge you on also is how it would work in, quote unquote, in real life. So the technical challenges that you might face. Does that make sense? All right. So Dirk, how should we do it regarding time?
I think so. The next class is on Wednesday.
Yeah.
So I think that could be the best opportunity to give feedback on the proposals.
Okay.
So that would mean, and of course you still have to read it. So that means that somewhere tomorrow.
Okay. So.
I mean, the first. So again, the first page proposal doesn't have to be really elaborate. It's just okay. This is how I think we should approach this.
Yeah.
And then we'll get some feedback on it, and then after that,
Yeah. So then, should we say tomorrow 4 p.m.?
Yep. Sure.
Is that tomorrow 4 p.m. for this 1-page proposal? Yep. One per team, and then I will correct them and I will send them back to you by Wednesday morning.
Yeah, that sounds good. And then after that, let's take a week to
for the final.
Yeah.
Okay.
I have a question. Is this for Dirk? Is this the 3rd graded assignment?
Yes. I'm sorry.
Oh,
indeed,
okay.
This is the 3rd graded.
Yeah. Okay.
Yeah.
Okay. So Dirk, how do we want to handle forming teams?
Well, you can do that by yourself, as far as I'm concerned. And my preference is that the teams mix with respect to the previous assignments.
Yeah.
But you know who your team was. So if you just email me again which team you are, then I'll handle the rest.
So please pick your teams in the next hour. That way we can send each team the description or the initial problem statement.
So do you have them here, the descriptions, or not? Very briefly, so they know what they can expect.
So what do we have to be preparing for tomorrow? Because we also have another presentation this week. So I don't know if it should be a lot or.
No. Just very briefly, just kind of what you think could be the right approach to do this. Yeah. That is fine, Björn. Yeah, because otherwise it will probably not match. But don't overdo it. That's. Yeah. So the in the end will be something like 3 to 5 pages, just like a report. But now, because we don't want to throw you in the blind immediately, so the idea is to first give a very short, just write down shortly your ideas how you think you could solve this. Then we'll give some feedback on that, and from that you can start working. That's the idea.
Yep.
And the only reason why there is a deadline for that one pager is because otherwise we don't have time to look at all of them before Wednesday. So that's.
So Dirk, should I show the outlines?
Yeah, I think that's good. Yeah.
All right, so you guys can have a look right here, and we'll send them to you right now, Dirk. So keep in mind, you're just picking teams, and then each project will be assigned randomly. Okay.
Wouldn't it be better if we just chose what project we want to treat?
Say that one more time.
Wouldn't it be better if this project was not randomly assigned, but that we choose which ones of these
Nope.
issues we want to
Nope.
treat?
No, that doesn't work, because yeah. No,
You don't want to do that? No.
Huh? Well, it's also regarding last year. So you said
For
that
one,
some students.
I would be really interested in the third project, and that's why I'm asking. It would be a lot more interesting than the other two.
Well, Dirk, that's up
I
to you.
think we can try Xavier. Why not?
Well, yes, but then what happens if certain projects have less and more candidates?
No, we'll know fast enough, right? I mean.
All right. Okay. Well, let's just say which projects. Say the 3 projects in order of preference, and we'll try and match the best we can.
Yeah, let's do it that way.
Okay.
I already made a group. So is it possible for us to just combine and then be assigned to a project? Or if we can figure it out ourselves, which project we want?
Okay. Make the groups, and in your group, decide state the order of preference of the 3 projects, and we'll do the assignment. We'll tell you then which one you can do. Okay. Dirk, can you handle the team formation and send me that once it's
Yeah.
Okay. So I'm only here today, but I am here if you have any questions on this assignment throughout the week. I'm going to post my email address in chat right now. So if you have any questions throughout the week, don't hesitate to write. I'll try and be as quick as possible in answering. Of course, if you send me something, 10 minutes before deadline, it's going to be a little bit difficult to answer in time for it to be meaningful.
Right.
Derek, could you please also answer some questions about the second assignment?
Sorry, one second.
Sure.
Okay, the document that Xavier is sharing is also on Canvas now, so you can look at there as well. I'm sorry, what was the question?
I'm a bit confused about the G and H questions.
Mhm.
I mean, I'm not really sure what was the question for G. I mean, I don't understand it. And also for H, I mean, the last question, you said that it's similar to the problem from Edwin's class.
Yeah.
Okay, so what I don't understand is how do we determine I0? So the initial, I mean, it should be somehow related to that power generated. That's for sure, but I'm not sure how we're supposed to determine.
Well, you know the units of intensity, right?
Sorry?
You know the units of intensity, I think.
Yes, it's watts over square meter.
Yeah, indeed. So you know, and you know the power. You know the power that is emitted by the light source. So then the question basically becomes over what area is that power distributed in the system, and then you have your incident intensity. See?
Okay. All right. So, and also, I'm guessing that the limits of the integral, of them is still 2 pi from 0 to 2 pi, and the other one should be from pi minus beta to pi plus beta, right? Because it's in the back.
Yeah, because you're looking in the backward direction now. So it's
yes. So then how do we determine beta? Because if we use the numerical aperture that we determined for point E, I think, not correctly, then beta would be very, very, very small, like 2 degrees.
That is true.
Okay.
And that just goes to show how very inefficient this whole process actually is. But that is the approach. Yeah.
All right. Okay. Thank you.
Yep. So whatever your answer you will get, it will be a very, very tiny fraction of what you put in. That's the thing with OCT, right? So it's a very tiny fraction of power that you actually get back, but because you have this huge reference arm that you basically use to amplify that signal with the reference arm. That's why it still works.
Okay. On that note, if anybody has any further questions regarding today or the assignment, please don't hesitate to write me. Thank you for listening. It was a lot of me talking. So thanks for toughing it out through that. Dirk, is there anything else I can do for you right now?
No, not at the moment. I don't think so. So if you guys would send me just send me an email, just like we did last time, what your group is and what your order of preference for the assignment is, then I'll compile that list later today, and then we'll send out the assignments.
Okay, great.
Am I missing still something from the chat here? Let's see. Yeah, so Björn asked, is it fine to work with one other person? Yeah, of course, because otherwise it will probably not work. Groups 3 or 4, I would prefer 3, but if it really doesn't work the other way around, then 4 is okay. Is there a group that can? So what do you mean, Manouk, with the question?
It's probably aimed towards the group.
Yeah.
Oh, okay, sorry. You have no group. Well, okay. Well, maybe you can try to get on a group of 3 then. I mean 3 or 4, but no, let's not make it bigger than that. Okay, then just send it via email, and then I think we're done for today.
Yep.
Other than that.
Sorry, one more question.
Yeah, go ahead.
Still about the second assignment. I'm not sure for question G. where are we using the volume fraction? I mean,
For G,
yeah.
well, basically in F, you calculated the efficiency of a single particle.
Okay.
And now the question G pertains the collection of particles, so all the particles together. So somehow you have to use the volume fraction to calculate how many particles there are.
So it's the volume fraction of the volume determined by the excellent lateral resolutions.
That would make the most sense, yeah.
Okay, thank you.
Without have to be careful not giving all the answers now, but yeah.
Trying to get as much as I can.
Yeah, yeah. Don't blame you.
All right, thank you.
Okay.
Okay, Dirk, one more question. What should we sign, of what should we, hoe zeg je dat, inleveren morgen? Don't know which project we have.
No, because if you all send me the groups as fast as possible, then I'll make the list of which group gets what assignment.
Okay.
Yeah.
Okay.
Okay.